Hello everyone, welcome to my channel. My name is Ors67. So I'd like to start off with story time. A couple of weeks ago, I was actually messing around with this random inequality. It was a totally standard contest one, nothing special, and I found something in it that was so bizarre. It was a phase transition, like the water turning to ice kind of phase transition. And yeah, I kind of haven't stopped thinking about it since, so I decided to share it with you guys. Anyway, hi, this is the channel Ors67. I basically just make videos about whatever math gets stuck in my head, and this one's been stuck for like 3 weeks. I plan on showing you the whole thing, including the weird part, the actual proof. No skipping the hard part, I promise. Let's just get right into it. So this is the original Nesbitt's inequality. You grab 3 positive numbers, make these 3 fractions, add them up, and you always land at 3 halves or higher. You don't need to take my word for it, you can just plug stuff in. 2, 3, 4 gives like 1.59. Seriously, pause the video and try to break it. You literally cannot get under 3 halves because this is a proven result. It's also known that you hit exactly 3 halves when all 3 numbers are equal. Each fraction is exactly 1 half, so 3 of them makes 3 halves, and that's the minimum. Now here's the interesting thing that kept me awake during history class. I decided to slap on a power on every term, let's call it alpha. Alpha equals 1 is exactly Nesbitt's inequality. But then I was like, wait, now how low can this thing actually go given any arbitrary alpha? As you'd expect, the symmetric case still gives something relatively clean, 3 over 2 to the alpha. But what if we move to the edges? Here, a equals b and c equals 0. Turns out the sum goes to 2, which is particularly nice in that it doesn't depend on alpha at all. With no intuition on how the rest of the cases look, I graphed both against alpha for some inspiration. Green's the symmetric one, gold's that flat 2. Interestingly, they cross right here at log base 2 of 3 halves, so the real minimum has to follow whichever's lower, the screen path, with an actual corner in it. And a corner in a minimum is already kinda sus, if you know what I mean. But what we can do is represent the same thing as a diagram where every choice of A, B, C is basically a point in this triangle. The center is the symmetric one, the edges are where a variable dies off. So where's the lowest point actually hiding here? For big alpha, yeah, it's the middle, but watch what happens when I shrink alpha down. Keep your eyes on the bright spot. You'll see that it jumps. It doesn't slide, it doesn't move, it just jumps, straight from the middle out to the edges. First time I saw this, I was 100% sure my code was wrong. In fact, it wasn't. The best explanation is that it's just discontinuous. It simply teleports. And by symmetry, it hits all 3 edges at once, not just one. So the to-do list is dead simple now. There are only 2 values the minimum could be, the symmetric 3 over 2 to the alpha, or the edge value 2. All that's left is proving nothing ever sneaks under the lower of the 2. Tiny bit of classic olympiad setup first, but it quickly pays off, I promise. Scaling all 3 numbers does nothing, it just cancels, so I'll force them to add up to 1. And now, b plus c is just 1 minus a, so every term only depends on its own variable. The whole sum splits into 3 copies of one little function. Let's call it g. Now, at the minimum, you can't make things better by shoving weight between the variables, and that forces all 3 slopes g' to be equal. If that feels hand-wavy, hang on, I'll actually show you why in a minute. Here's g', always positive, and honestly, its shape is the thing that does all the heavy lifting. Just look at it. The graph shoots up at both ends, dips once in the middle. It's a valley. Down once, up once. That's it, that's just the whole trick. If we slide a flat line across the valley, it can hit in 2 spots max. So at most, 2 different x's can ever share the same slope. But here, A, B, C all want that same slope. 3 of them 2 slots, somebody's gotta double up. So at least 2 of them are forced equal by the pigeonhole principle. And boom, that's the whole point. 2 of them equal means the search drops from a 2D triangle down to a single line. If you know Lagrange multipliers, feel free to skip ahead. But for now, let's forget we have 3 variables. Let's just do 2, a and b, that have to add to some fixed budget. I want to make g of a plus g of b as small as I possibly can. Now we have 2 points on the curve. The goal lines are the slopes at each one. And that number up top is the total I'm trying to shrink. Now here's the interesting part. If we move a tiny bit of weight from a over to b, Whether the total goes up or down literally just depends on which slope is steeper. So if the slopes don't match, there's literally free money sitting right there on the table. So therefore, we only stop when the slopes are equal. That's when there's nothing left to grab. And that's the whole Lagrange multiplier's idea. But with three variables, that's also the exact same thing. All the slopes must match. Cool, let's get back to the original problem. Okay, so on that line, a equals b equals k. One substitution later, and the whole problem is just this one curve, h of j. Three things to know about it. The middle's the green value, the right end's the gold 2, and the left end just blows up to infinity, so it never really matters. So really, it's just the green versus the gold. That's the entire fight. Now watch it move as alpha drops. The middle valley lifts up, flips into a bump, and a new valley sneaks in from the left. Figuring out exactly where that flip happens, that's next. We start by taking the derivative of h. It looks gross, I know, but factor out one positive chunk and that chunk's just decoration. It's always positive. Only the bracket actually matters. So I'll just name the bracket big H, and now the annoying question, where is little h flat, becomes a baby question. Where does this little bump cross the line 1? And now big H is the nicest function ever. 0 at both ends, 1 bump. Two things I absolutely love about it. It's exactly 1 at the center for every alpha, and its peak sits right at 2 alpha over alpha plus 1. And quick before I show you, does the center stay the lowest point for every alpha? Feels like it has to, right? Watch the peak as I drop alpha through 1/3. Turns out it flips. When the peak's right of the center, big H is still climbing as it passes 1, so the center's a minimum. When the peak slides left, big H is already falling, so the center turns into a maximum. The symmetric point literally changes the personality at 1/3. For alpha above 1/3, the center really is a local min, which means the answer is just the smaller of our two guys, and they swap at log base 2 of 3/2. That's everything above 1/3. Done. But okay, here's the part that's somewhat troubling. There's two special alphas, and they're not the same number. 1/3 where the center flips, and 0.585 where the global answer jumps. 1/3 is smaller, so there's this gap. And in that gap, the center's still a real valley. You could drop a marble in, and it just sit there. But it's not the lowest anymore. Safe locally, but beaten globally. Physicists call that metastable, and we're about to actually feel what that means. Now, below 1/3, the center's a bump now, and the real minimum's off at some point J1 to the left. And this is where I got stuck for like 2 days straight. There's no formula for J1. You literally can't solve for it. But you also don't really need to know what exactly J1 is. You just need to know h of J1 is 1, and that one fact is enough to kill the ugly term and crush the whole value down to this. I stopped chasing J1 and did a kind of cheat. Instead of proving the bound at that one annoying point, I proved it for every single J at once. Harder technically, but now I don't need the number I can't even find. And the right side only grows as alpha grows, so the worst case is alpha equals 1/3. Beat it there and the rest is free. So if we plug in 1/3, clear the gross fractional powers, and the scary thing collapses into a plane cubic. P of j just has to stay above 0. And it actually does, quite easily. It only goes downhill here and bottoms out at 11/8. So that off-center minimum is at least 2, the boundary wins, and the hard case is finally done. Now let's slightly retrack and make that metastable thing actually physical. We read the curve as a landscape. Let's drop a marble in. Big alpha, 1 valley, dead center. The marble just chills there. That's the symmetric solution. Now drop it past the threshold. The right edge sinks lower than the marble's valley, but the marble has no clue. It's still stuck in the middle. It needs a push to get over the hump, and that's literally super cooled water. Below freezing, it's still liquid, because nothing's kicked it yet. But if you drop it below 1/3, the floor under the marble caves into a hill. Now it can't even stay. It rolls off, and the true minimum's way out at the edge. The symmetric state froze out. And if we stitch both cases together, there it is, clean. Above the threshold, the symmetric value, below it, a flat 2. And plug in alpha equals 1, Nesbitt's 3/2 just falls right out. It was the tip of the iceberg all along. But what happens if alpha is above 1? Well, that's the easiest part. We just use a simple power mean argument plus regular Nesbitt's inequality, and it just hands you the symmetric bound for free. So this whole thing works for every positive power. And here's the entire story in one shape. H plotted over both the shape J and the power alpha. Every slice front to back is one of these curves we kept staring at. The red line's the minimizer. Big alpha, it rides the middle crease. Then it just leaps to the wall and stays. That one clean break in a smooth surface, that's the phase transition. There it is, in 3D. Okay, maybe the reason why I can't let this go is, this exact shape, a symmetric answer losing to a lopsided one past some threshold? It's everywhere. A beam buckling, magnets snapping into line, bubbles in boiling water. And you just met it in a classic contest inequality. Maybe an extension of it. So yeah, that's the entire proof in one video. One symmetric guess, one clean cut from 3 variables to 1, one little bump, and a phase transition that was just sitting there the whole time.